Assalamu alaikum. My name is Muhammad Abad Khan, and today I'm going to be explaining the examples and trying to simulate them on Proteus. This is our chapter 7 of our AVR book, and the chapter's name is AVR Programming in C. Here we have a few objectives. Examine C data for the AVR, code C programs for time delay and I/O operations, code C programs for I/O bit manipulation, code C programs for logic and arithmetic operations, code C programs for ASCII and BCD data conversion, code C programs for binary hex to decimal conversion, code C programs for data serialization, code C programs for EEPROM access. So, why program the AVR in C? Compilers produce hex files that we download into the flash of the microcontroller. The size of the hex file produced by the compiler is one of the main concerns of microcontroller programmers because microcontroller have limited on-chip flash. So the thing is, we have limited amount of data, limited amount of space on our chips that are on our microcontrollers. So it is, easy to compile, and it is better to compile on these in this language in C. We can efficiently use that space, that storage on our microcontrollers. So here this table is really important because we have some data types, their sizes and their ranges that we have to use appropriately. So first of all, we have our unsigned char. It is of 8-bit and its range is from 0 to 255. Then we have char. Its size is in 8-bit. It goes from -128 to +127, and the list goes on. So let's start with our example number one. Our example number one says write an AVR C program to send values from 00 to FF to port B. So in here, first of all, we include the header file. uh, this header file tells our compiler to perform the input output operations on our AVR. It is a standard AVR header, and then we have our main function. Because we are not returning anything, the parameter is void. If we leave it empty, it means the same thing. Then we are basically initializing, or you can say we are determining a variable here of unsigned char, and we are naming it Z right here. Then we are giving our DDRB, our data direction register of port B 0xFF. This means that uh, our data register will be getting FF, which is all high values. So right here, FF means that it will have 1 1 1 1 and then 1 1 1 1. So our data register will be getting this value, which means all high. So all of the pins of port B, which are 8 pins, will be high. uh, right. So all of the pins will be getting high, and then we have a for loop which is going from 0 to 255, and because it says less than or equal to 255, so it will go from 0 to 255, which basically will complete 256 iterations because it is going from 0. So it will complete our 256 iterations here, and it will display that data on port B. Now obviously it cannot display the data in decimal, so what it is going to do is it is going to convert that 255 or all those values that it will have into binary. It will convert all this data into binary. So let's say for 1 it will say 0 0 0 0 and then 0 0 0 1. So this will be for 1. and so on. It is going to convert it all into binary form, and then it is going to display that binary on port B. uh, and we can simply connect some LEDs on these ports, and check them that if it is giving us the correct thing or not. So we'll move on to our Proteus here. I have made this Proteus. It was very simple to create. We just simply made a new file, and in there we selected our AVR chip, our AVR328P chip, that is also mounted on our Arduino Uno, and simply connected an LED with this chip. And then I went into the source code. In here, this was present already, and I just had to add the same code here. This is the standard library that I talked about. Then we made a function called avoid e71. uh, this simply shows that it is our first example e71, and it is the function is of void data type. In here, it's this is the same code that I just explained. And then I made another function for delaying this function for delaying this. What I did is I simply made a function named delay 100 ms, and simply just made a variable called I, and simply just placed a loop on it. But this loop isn't really working. We can see that the code is working correctly, because this is changing, but it is doing it really fast, so we cannot see on this LED. So this is our example number 1. Now let's move on to example number 2. So this is our example number 2, and the thing is, we have to copy our code from this website, but this website is having currently it's having some issues, and we can't really copy code from here, so it won't be easy with making all the code, copying it and placing it into Proteus. So now we have our example number 2. In here, first of all, we have our standard library. We have our main function. This time we are making uh, a, a string here. So what we are doing is we are creating a string using these quotations right here, and now this is acting as a string. What is a string? It is a sequence of, or a collection of, characters. So we our compiler will treat this as a string, and it is kind of like an array, but this is obviously for a string. Now what happens in an array? We are giving numbers to we are assigning a number to an index. So the number, when it will be printed, it will be printed in binary form, but in here, because we are using a string character here, it is going to be converted into its ASCII, and that's what our question is saying. Write an AVRC program to send hex values for ASCII characters of this to port B. So we are simply again making the character here, unsigned char, naming it Z. Then we are making port B as output, as I explained before, by giving it all high or 0xFF. We are making it uh, you know output, and afterwards we are again just simply running a loop here. This time our loop, as you can see, that it is going from 0 to 10. Now why is it going till 10? Because of the length of our string here. And then we are simply just uh, outputting this string and giving it z. So when the z will have value 0, it will go 0 here, and this 0 will move on here, and it is going to print the value of 0 in ASCII to port B right here. And if we want to see what that will be, we can just simply Google ASCII table, and there are a lot of these tables available on the net, and we can simply just open it up and see what's the value of 0 in ASCII. uh, Here it is. Its ASCII value is, its ASCII value is 0 actually here. um, Let me just show you guys another table. These aren't showing the ASCII values, but you get the point that we can simply just search for an ASCII table, and from this ASCII table we can see the values. Here this one will show the value, I'm pretty sure. um, so right here it will, I think, print this 48, but this will simply print the ASCII value for this function. So let me just run this function. Let me just write this code into Proteus. So I just simply wrote this code into my Proteus here, and when we want our function to work only once, we'll just simply put this while loop here. Now let's recompile the code. Here it will rebuild the solution, and it will check if there are any errors in this code as well. If there are no errors in this code, now it is showing an error because of the return 0. Let me just remove this and rebuild the code. Now it compiled it successfully, and we can just simply, so we can see here that it is giving us the value of 0 in ASCII. Now obviously we cannot really display that value on an LED here, but we can see that it is working. Now let's move on to the next code. And with those red and blue LEDs, we were seeing that it was displaying a code. Now obviously there's a delay in there, so it is going to take a while to change. uh, let's move on to our example number 3. um, Here it says write an AVR C program to toggle all the bits of port B 200 times. So let's start. We have our standard AVR library, we have our main function, we are making port B as our output, we are making uh, we are giving that data direction registers 0xff, which means we are making port B our output. Now we are giving port B a value to display, so that value is 0xAA, which will represent which is represented in binary by 101011010. Again we are making a character, we are naming it Z. Here we are again making a loop right here, and what this line says is toggle. Simply it means toggle. We are giving the not of the not of port B back to port B, so it is simply just switching between the values, uh, because once it is saving the first time it is saving 1, the second time it is saving 0, and it is simply just toggling between these values. Let me just write this code in Proteus very quickly. So here's the Proteus. I just simply wrote the code, and this time I removed the while one because it was only making the code run once, and we obviously want it to run continuously. Now currently there is no delay on this, so it is going to be really fast, and it compiled quickly, and we can see that it is actually toggling the values. We can see that uh, port our pin 12 is turning on and off, on and off, on and off, but it's doing it really quickly because there is no delay on it, so we cannot obviously see it. The delay function, I don't know why it is not working. We can try again obviously, but it is not working at all. We can rebuild the solution. Yeah, we can see that it is really slow. Let me just decrease the time a little. It wasn't working before, and now it is working all of a sudden. Now let's see here. It's still really slow. Let me just decrease the time. Thing is, in Proteus, I have a Proteus 9 here. It has a lot of bugs in it, so it causes a few problems. Sometimes the functions doesn't work. Sometimes. Now here we can see that it is toggling. It is again doing it really quickly, so we cannot see it, but it is toggling. So this is our example number 3 here. Let's move on. Now we have to go to our example number 7 dash 9. So here is our example number 7 dash 9. uh, this says LEDs are connected to pins of port B. Write an AVRC program that shows the count from 0 to, again, this dollar sign FF just basically means that the value is in hex, and it is the same as writing it as 0x FF. So this 0x simply means this dollar sign. So it is also displaying the value in binary here. It is in 8-bit on the LEDs. So this is simple code. We just have a few header files here. uh, we have an AVR header file. Simply we are defining our CPU speed here, then we are giving it a delay function here. This function, what this library basically does is give us the power to use this function right here. And we are simply we have our main function, we are making our port B output, we are simply turning on a loop, and in this loop we are just uh, giving our port +1, and we are saving that value back into the port. So it is simply just, you know, making the same for loop, uh, but here we are uh, using the same functionality using while loop, and we are just simply, we have put simply a delay in here. So let me write this code into Proteus. So we just simply put our header files in here, and then we simply wrote the same code here. Now let's see if it has any errors or not. So it compiled well. So I think this is switching really fast. Oh, here we saw that it moved to the other pin. So it is working correctly actually. We can see that it has uh, moved towards pin 13, and now both of them have turned on. So it is simply now it says 2 basically in binary, and now it is going to, sorry, it says 3 in binary. Now it says 4 in binary, because 4 means 000 and 0100. Now it is going to go towards 5, which is 0101, and we can see that it is basically replicating the binary code here. So this was 7-9. Let's move on towards the next example. uh, Now we are going to do 7-11. Here we have 7-11 here. Here the question says write an AVR C program to get a byte of data from port C. If it is less than 100, send it to port B, otherwise send it to port D. So In this program we are also taking some input. First of all, we have our standard AVR library. We have our main function. Here we are making our port C as input. We should have wrote 0x00 here, but 0 means the same thing. We are making port B and port D as output. We are simply defining a variable named temp, and it is of character data type. Of unsigned character data type, we are simply writing a loop here, and we are saving the value. We are reading the value from pin C and storing it in temp, and we are just simply applying a condition here. It is checking if temperature is less than 100. If it is going to send that data to port B, and if it's not, it is going to send that data to port D. This is a very simple code. Now let me just write this code into Proteus. So here this is done. So this is the same Proteus. We don't need these upper libraries, so we are not using them. Uh, we can actually use the delay here. Actually, don't need this one. Um, but here basically we are just taking the input. So let's build the code. Let's see if it has any errors or not. And it compiled successfully. Now here we can see that our port C, which is right here, is showing gray because it is our input, so we have to give it some input here. Can just give it high here using this. So now it is basically getting 5 volts here, and we'll just turn it on. So we can see that because it is getting a high value, it is sending that value to port B right here. And let's say if we put a resistor in here, which is basically going to top the voltage here, the value will be reduced. Actually, it's probably going to go 10k is too much. Let's go 200. I think it's the value is still above 100, so it is simply just sending it to port B. But that basically explains the code that is working. It is sending the value to port B. Now let's move on to our example 7-12 here. Here it is. So here what the question says is run the following program on your simulator and examine the results. Oh, so we just have to run this code here. We have our standard library, our main function, and we are making port B as output, port C as output, port D as output. We are simply uh, ANDing and ORing these hex values here, and we are XORing these hex values. Then we are inverting these hex values using the NOR function. This is the XOR function. This is the OR function. This is the AND function. And then we are simply just we have a loop here, and we are returning 0 back. So let's simulate this value and see what the simulator does. Let me just write this code in Proteus. So because we have uh, a while function here, it is only going to work once. And here, this is the code. Simply just wrote it really quickly, and let's just rebuild the function. Let's see if it has any errors or not. It compiled well, and is simply showing data on all of these pins. We can see, let me just make a few copies of this and put it around here. See which pins are working. 32. Let's just name it 32. Give this 32 here. One of these ones were working as well. 25, it is working. 25, 25 here, and we don't really need this one. And 13 here. Alright, so let's leave that one. So we can see that the result of XOR and OR and inverting and that ending is giving us our results here. So simply those values are being AND here. We can change those values as well to get different results. Let me just put it right here. We can change these values and can say 37 we can make it. We can simply just rebuild the code again. And after it is done, we can just simply check, and it will affect this one. So it has affected it. It has changed these ports. So this was example 7-12. Now let's move on. Now let's see example 7-17 very quickly. This is our example 7-17. What the program says is write an AVR C program to read pins 1 and 0 of port B and issue an ASCII character to port D according to the following table. When pin 1 and pin 2 both will be 0, it will send 0 to port D. When pin 0 will be 1 and pin 1 will be 0, it will send 1 to port D, 2 and 3 with the condition. Now let's just write this code into Proteus. So here we have just simply wrote the code here, and now let's just rebuild the library. Now this code is basically doing the same thing. We have just initialized or defined a character here named Z. It is an of unsigned uh, char data type. We have made our port B our input, our port D our output. We have simply created a while loop, and we are giving Z the value of our pin B. So it is basically reading from pin B, and it is going to end it with basically 3 0x. So this basically means 0x 03. It is ending it with this, and then it is applying these cases that if port B reads 0, we are simply going to give port D the ASCII of 0, like I showed in the ASCII table before. So let's just run this code. Now here we can see that it is not showing anything obviously, so we have to first of all give it some output. Now we have given it an input, sorry, and it is showing an output here. Now this is basically the ASCII of uh, 0 sorry 1 right here, because we are giving it I'm giving 1 on pin 1. So if I give 1 on both of these like this, now we can see that the output has changed. We have to ignore this one because obviously it is connected with this, but here it has changed output. So let's move on. Now we have 7-24 right here. So what this program says is write an AVRC program to get the status of bit 5 of port B and send it to bit 7 of port C continuously. So this will work as kind of like a real-time program. It will be checking on uh, bit 5 of port B, and it will sending it on uh, bit 7 of port C continuously. So we have our standard library, we have our main function. We are simply just you know uh, reading the data from uh, bit 5 of port B, because it is we are making it as input. And what this function does right here is it is masking it. So this basically means that our ddrb is actually ddrb is being ended with not of. Now here what we are doing is we are masking the bit number 5 of port B. We are making it input with this. And what this not mean is we are masking it as 1, but this not will convert that 1 into 0. So it will be converted into input for port B right here. And here we don't have a not, and we are ORing it with our port C. So what we are doing is we are making the bit 7 of port C as output. And then we simply have a loop here. In this loop we are checking if we are getting an input on our pin B, which is of bit 5 pin B, and if it is getting, we are just simply giving that data to ports of bit 7 of port C, and simply if we aren't getting anything, we are just clearing that bit. So let's just write this code into Proteus and see what the output will be with that simulation. So the Proteus is ready. uh, I have explained the code. Now let's just rebuild the code and see our output. It has compiled successfully. Now we have to see that simply the this is the bit number 7 of our port D. Sorry, we are using port C here. So um, this is the bit 7, I think. I think this code is working correctly. Bit 5 of port B is input. So here we can see that uh, when we are giving it an input right here. I think this we aren't getting any output here. I don't know why this code is not working, but let's move on to the next code from the book. This was 7-24. Now we move on to 7-25. A door sensor is connected to the port B pin 1 and an LED is connected to port C pin 7. Write an AVRC program to monitor the door sensor, and when it opens, turn on the LED. Uh, we simply have our headers here, 3 headers. We are just simply defining the pins on our sensor, on our microcontroller, that our sensors will be connected here. So we have our main function. uh, we are simply again masking and showing that this this pin will be acting as input, again doing the same masking and showing that this pin will be our output, and we simply are doing the same if else function and seeing if there is any type of input here. If it is, then we are showing the output. If it's not, we are just simply clearing it. So let's run this code on Proteus and see how well it is going to work. We will move on really quickly from these ones, and I'm just going to give an overview because the video is being way too long. So here the code is ready. Let's rebuild it. And here what, as I told you, that what this simply means is uh, the pin 7 on our port B is acting as input. And here what this means, that our port C, our port C's pin 1 is acting as our output. So we have compiled the code here. So pin 7 of our port B is right here, and then pin 1 of probably right here. I don't know why this code is not working as well. It's probably because we are taking some input, and these codes uh, don't really work in simulation that well as well they work in, obviously, with some hardware. We will just move on to 7-26 now, and 7-27. Here we have 7-26. It says write an AVR C program to convert packed BCD 0x29 to ASCII and display the bytes on uh, port B and port C. Now these two codes we cannot really simulate. It takes time to simulate, so we aren't going to simulate these ones. We are just going to I'm just going to explain these codes, and we are going to move on from this and go towards finalizing the video. uh, Here we have our standard header file. Right here we have our main function. We are simply declaring two characters here of unsigned char data type x and y. We are simply initializing another variable here, or called my byte of, again, unsigned data type, unsigned char data type, and we are giving it the value 0x29. What this simply means is 0 0 1 0, which basically means 2, and then 9. uh, so let's move on from this. The 9 is simply in ASCII, so sorry, in hex. So then we have our data register B, C, we are making it output. We are simply ending the my byte variable with um, 0x 0f. So this f will be ended with this 29. So here we will have 0f. So this 0 will be ended with 2. So obviously that 2 will be removed, and it will be just 0, and then this f will be ended with 9, so it will make 9 right here, like shown here before, right here. And the same will be done with we are ORing this x with 30. So what it is going to do is it's going to just simply give us x back with 3 here. So we need 3 and then 0 here. So we are, you know, because we have this result 0x 0 9 saved in x, so we are ending ORing it with our 0x30 here. So what it is going to do is it's going to make this 0x39 for us, and then we will use that and simply then do the same with the y here and display those on port C and port B here, and it will simply just show the bytes. Let's move on to question number 7-27 here. It says write an AVRC program to convert ASCII digits of 4 7 to packed BCD and display them on port B. Again we are doing the same thing. We are declaring a variable here. We are initializing two more variables. These will now have ASCII values in them, as I showed from the ASCII table here. These will have ASCII values in them. So then we are making our port B as output. We are simply ending W with this. So what we saved in W is 4. So that ASCII 4 will be ended with this 0x0f, and it will mask out 3 here as it says. Then we obviously left shift it by 3, and we make it upper BCD, and we do the same with Z, and we just OR both of these and we just display their value on our port B. So this is a very simple code. Let's move on to 7-31 now. This is 7-31. What it says is write an AVRC program to convert this value in binary FD in hex to decimal and display the digit display it on display the digits on port B, port C and port D. So we simply have our standard library, our main function. We have declared a lot of variables here. Char x, uh, unsigned char x is the variable, bin byte is the variable, d1 is the variable, d2 is the variable, d3 is the variable. We made all three ports B, C and D as output. uh, we are displaying this hex value. We are inputting this hex value. We are giving this hex value to the bin byte. We are simply dividing that value by 10, and then we find its remainder and we save it in D1. Then we find its remainder again, save it in its middle digit basically, save that in D2. Then we divide it and save that in D3. This will be the most significant bit, or most significant digit that we can call it, and we are simply displaying this value on our port B, C and D, and we are returning 0. So this was a very simple code as well. Now we move on to our last code. It is 7-34. What it says is write an AVRC program to bring in a byte of data serially, one bit at a time via port C and pin 3. Port C's pin 3, and the least significant bit should come in first. So we have um, our standard header file here. We are declaring the serial pin of pin 3, and this will be in port C. This pin will be in port C. We have our main function here. We have the unsigned char here, our basically declaration of the variable x. We are initializing another variable here of unsigned char. We are naming it rega, and then we are simply again making this bit as input, as I explained before. We are simply using masking here and not operation to make it input. Then we have a for loop, and it simply goes from 0 to 8, and here we are just simply left shifting that bit one by one, which basically makes it a serial input. And again we are just simply copying those bits from LSB to MSB, and we are simply just displaying them. So this was chapter number 7's examples. uh, Thank you for watching the video.